Projecting a point onto a line. Now, calculating the distance from a point to a line is a staple in the first unit where you do vectors, lines, and planes in a multivariate calculus course. Typically what's sought is the distance, and that's the norm of a projection. But the projection of the point itself is not often considered. So in this webinar, we're going to look at several different methods for obtaining the projection as a point. We're going to look at the projection of a point onto a line, and then onto the intersection of two planes through the origin, and then onto the intersection of two planes not through the origin. Orthogonal projection and even a non-orthogonal projection are going to be used. All of the calculations and all of the visualizations are done in Maple, and without Maple, none of this stuff could have been done or would have been done. Let's begin by projecting a point onto a line. So here's a problem. Project this point onto this line. This is the vector A. This is the direction of the line, so that's vector V, and this is a point represented as a position vector. So here's our first solution. We'll work in the student multivariate calculus package, and we'll make use of some of the lines and planes tools in that package. So we define the vector A, the vector V, we define the line, and the point that we want to project as a point. And we can use the projection command in that package, project P onto L. This is the answer that we're going to be looking for. It is the point on the line that is closest to the point P. An analytic solution using the tools of the calculus would run like this. We need equations of the form x equals 3 minus 2t, y equals z equals. So we could get that by one of the tools in the multivariate calculus package. You get the representation of the line in parametric form, and you get a list of the equations that you need. The distance between an arbitrary point, x, y, z, and the projection point, if evaluated with x, y, z using these equations, you get a function of t. Differentiate that with respect to t and solve. You said equal to 0 and solve. You get this value of t. Take that value of t and put it into these equations, and you get the equations x equals this number, y equals that number, z equals that number. And if you do a substitute into, and I used this substitute into, and I substituted it into xyz, and we have again recovered the point of projection. The vector solution that is most familiar to people coming out of a multivariate calculus course relies on this diagram. The red line is the line that you want to project onto. This dot, I think it's blue, that you want to project onto the line. You see that green line helps you visualize what's happening. This is the origin. This is a position vector to the point on the line that you select, and typically it's taken as the point A. This goal vector is the direction vector of the line, and you connect this point A to the point to be projected. That's the red arrow. That's what gets projected onto the goal vector. It happens to be pointed in the other direction. This is the projection. This blue vector is the projection. This point, for which the yellow vector is the position vector, is what you're after. And how would you do that here in Maple? W is this red vector, and it is the vector P, so that's a position vector which you don't see, minus A. So that's the red vector. You project that W onto V, and this is V, the goal vector. And so it's W dot V over V dot V. And then you add back A to get to this point, so that you have vector addition. The black vector plus the blue vector is the yellow vector, and the yellow vector is the position vector to the point, so its components are equivalent to the coefficients of that point. The next thing we want to look at is obtaining the line of intersection of two planes. So here's an example. We have these two planes. We want to get the line of intersection. Now, typically, what's done in the multivariate calculus course is you get the direction of that line by taking the cross product of the normals. So look at this figure 2. You have a green plane and you have a red plane. This green arrow is normal to the green plane. The red arrow is normal to the red plane. Here, I can move this around. You can see that a little bit better. Okay. The cross product is the direction vector for the line, and then you get 1 point on the line on the intersection of the two planes, and you can get the equation of the line. But there's this other picture, figure 3, that I want to call your attention to. This is the line of intersection of the two planes. This is the direction vector of that line. These are the two normals. You see, here are the two normals. Those two normals span a plane. That's what this plane here is. It span a plane. And that plane is orthogonal to the line. That's the image that will be used eventually in our further discussions. Okay, so here are the two normals. Cross, get the direction vector for the line. But think of these two normals as spanning a plane orthogonal to the line. One way to get the equation of this line of intersection is to use the tools in the Student Multivariate Calculus package. So I did a restart to clean everything up, bring in the package, define the two planes. So these are plane objects, manipulate them. There is a get intersection command, or you could use the line command, because these two planes determine a line. This could be replaced with the line command. Having obtained the line object, you ask for the representation of that line, and you can get it returned to you in different forms. The combined vector form is the one you're most familiar with. 3/4 minus a half, 3/4. That's the point, probably this point here. And then the direction vector is 2, 0, minus 2. An alternate way to get the equation or a representation or parameterization of this red line here, you have two planes. So that's two equations in 3 unknowns, which means you can solve for 2 of the variables in terms of the third. So solve the 2 equations for, say, y and z, and you will get x is the parameter, y of x is this, and z of x is this. So this is a different parameterization, but it's still a parameterization of the line. Now let's get down to business here. I'm going to project a point onto the intersection of two planes. We'll first look at two planes through the origin. So here's the example. Plane 1, plane 2, find the point on the intersection of those two planes that's closest to the point 1, 2, 3. So you're going to have to get the line. At some point, you're going to have the line of intersection, and then you're going to project onto the line, as we saw earlier. A very simple solution using the tools of the multivariate calculus package. Again, a restart, bring in the package. Define the two planes, but not as equations. Use the plane construct to construct a plane token. As we saw earlier, you could use get intersection, or just the line represented by the intersection of two planes, and then project 1, 2, 3 as a point onto the line L, and the return is the point of projection. An analytic solution is also possible using the Lagrange multiplier method. Well, there's a Lagrange multipliers command in this student package. We need the objective function, the constraints, and the variables. And what is the objective function? Well, it's the distance from a point, xyz, to the point to be projected, 1, 2, 3. It would be square root of x minus 1 squared plus y minus 2 squared plus z minus 3 squared. So that's the objective function, easily set up here with this distance function, the constraints. And the reason for writing these as not equations is because this Lagrange multipliers command does not want equations. It just wants these functions. And the return is the projected point. And now for a vector solution. Figure 4 captures the essence of the vector solution. We have the red line. We have the direction vector for the line. That's this goal vector. We have a point on the line. Because the planes that we intersect go through the origin has to be on the line of intersection, so we can take this point to be the origin. Now, these two blue vectors are those normals that span the plane orthogonal to the line of intersection. The black vector is the position vector to the point that we want to project. So it's the point 1, 2, 3. The red vector, the round red vector, is the projection of the black vector, 1, 2, 3, onto this plane. So let's look at some of the stage directions that we have here. So we have the line L. It's described by the position vector TV because it goes through the origin. And you can think of it as a subspace. The goal vector, well, that's the direction vector, but I had to scale it so that this diagram wouldn't look terrible. The plane that you see here is orthogonal to the line. The round black vector, that's the direction vector to the point that we want to project, and I call that U. And that the point is 1, 2, 3. Now, this symbol means the projection of U onto M. That's the green vector. Now, it can be found by projecting U onto the plane. You get the round red vector. Then you get the orthogonal component or the orthogonal complement, and you get the green vector. The point that we're trying to find is at the tip of this green vector. We need the component of the black vector orthogonal to the plane. So we're really looking for the projection of the black vector onto the gold vector. It turns out to be this green vector, and the coordinates at the tip of the green vector are what we're looking for. Now, the red vector is the black vector minus this projection. The two normals span the plane. So if you take a linear combination of these two blue vectors and choose that combination appropriately, you should be able to get the red vector. And so the red vector that I get as a linear combination of these two normals, I've drawn as a flat black vector. And since they lie on top of each other, it's very hard to see that you have two vectors that you got from two different ways. So I'm going to look at three different techniques for getting this orthogonal component. So the first way to get the green vector is to project the black vector onto V. Project this onto that. You'll get the green vector. That's the most direct way. Second, project U, that's the black vector, onto the plane and get the orthogonal component, and that'll be the green vector. And the third way is to get the green vector as U minus its projection in the plane, which is obtained as a linear combination of the two blue vectors. And this is the linear combination. So here, the calculation requires that you find appropriate coefficients A and B. So here are the three ways for getting that green vector. Project U onto V. So here's U. V is the direction vector for the line, so an easy way to get that in Maple, using the tools in the multivariate calculus package, is to say, get the direction vector. Then project U onto V. Now I put a transpose here so it would print out horizontally to save some space. There's no commas. That's a typical, this is a row vector. A Maple list would have commas in between. The second method projects U onto this plane and then gets the orthogonal component. So we need the plane. Well, it passes through the origin, and its normal is the direction vector V. The projection of U onto the plane, okay, projection U onto the plane, that's the red vector. And then by subtraction, you get the orthogonal component. And again, I printed it out horizontally and clearly see they are the same. And finally, let's get the projection of U onto the plane as the flat black vector, the linear combination of these two normals. So what's involved there? Well, we want the two normals. You can use the get normal command in the multivariate calculus package. It'll go to the plane object, get the normal. Here's the linear combination. You subtract that linear combination from U, and what's left is the orthogonal component. Okay, so black subtracted from this is that. So how are we going to do the calculations? Well, we've got to find A and B. So take this vector, which I call Q, dot it with each normal. Now, this vector is really the green vector. And the green vector is orthogonal to the plane because it's along that line, which is orthogonal to the plane. So the green vector is orthogonal to each of the two blue vectors. So dot it with N1, dotted with N2, two equations that will determine A and B. Here's your solve command. Here are your values for A and B. Well, if you put those values for A and B back in here, you get the point of projection, the projected point, the tip of the green vector, which we have seen several times already. Now let's project a point onto two planes that don't pass through the origin. And there are two examples of this. So in our first example will be in R3. I'm going to project this point, 1, 2, 3, onto the intersection of these two planes. Because they are non-homogeneous equations, they don't pass through the origin. I guess the word affine could be used in here, but I'm not going to do that. Preliminaries. Bring in the student multivariate calculus package and alias student linear algebra to the name LA for convenience later. U, this point, as a position vector, and here it is as a point. These are the constraint expressions. Everything goes to one side, no equal sign, because I want to use that in the Lagrange multiplier command down here, which doesn't want you to have an equation. Normal vectors to the two intersecting planes. The Lagrange multipliers is applied to an objective function, which is the distance between a point and this given point. Given as a vector, I take the norm. That will give me the distance, constraints, outcomes, the point on the line that satisfies these two constraints, and it comes out as a list. Now we can make use of the multivariate calculus tools, define the planes. They together define the line of intersection, so use the line command, and then we want to see what that equation looks like. So we get the representation of that line in the form of the vector, non-combined. So this is the direction vector, call that V, and this is a fixed point on the line, call that A. So grab that point A. It will come back as a list. I'm going to use get point, and I convert it to a vector. The direction comes back as a vector, and W is the vector from A to U. So from the fixed point on the line to the point that's being projected, and here are those three vectors. You can see A matches, V matches, and this is W. We're going to do this projection in several different ways. The first way is to project this vector W onto the plane containing the point and the line. Well, it needs a figure 5. Okay, so this pink plane, that's the color I used when I constructed this, it contains the line and the point to be projected. So green here is going to get projected. This is the line. This is the origin. This is position vector. This blue vector is the position vector from the origin to the point A. And this is the vector W. I think it's brown. So I want to project W onto the line. That's going to give me the green vector. But in order to get the coordinates of the tip of this green vector, we've got to use vector addition. When I get this component of W on the line, it comes back as a vector at the origin. It doesn't come back as a vector on the line. It comes back as a vector at the origin. And so the vector addition I have to perform is this black vector plus the blue vector. So the black vector is parallel and equivalent to the green vector, just that it's located over here at the origin. So by adding the black vector and the blue vector, so this is actually the black vector, and this is actually the blue vector, I get the yellow vector, which points to the tip of the green vector here, the projection, that black dot. The components of this yellow vector give me the coordinates of this point of projection. And let's take a quick look over here. Minus the fourth, minus a half, 7/4. Minus a fourth, minus a half, 7/4. Second method is to project U onto the plane orthogonal to the line L. Okay, here's a picture, figure 6. Here's the line L. This is the origin down here. The goal vector is the position vector to the point rho that we want to project. This gray thing here is the plane orthogonal to the line L, and it's spanned by the two normal vectors, which are not shown. The green vector is the projection, the goal vector, down onto that plane. The orthogonal component is this black vector, and then by vector addition, we add the black vector and the blue vector, which is the same position vector to the point A. That gives us the yellow vector. Tip of the yellow vector has the correct components, which are the coordinates of the point of the projection of the green onto the black. So the computations are done this way. Here's where we use that call to linear algebra. We construct a projection matrix on the plane spanned by those two normal vectors. So that gives us this projection onto this plane. So U minus the projection gives us the black vector, the orthogonal component. We add A, and we get minus a fourth, minus a half, 7/4. At this point, I found it useful to draw a picture showing the two planes we used in these projections. So these vectors haven't changed their meaning. This is the position vector to the point rho. Its projection down onto the orthogonal plane. This is its orthogonal component. This is the origin down here. This is the position vector to the point A, fixed point on the line. The yellow vector is the sum of the black and the blue. This is the plane onto which we've had the vector W here to here. I didn't draw that, but the glimpse of these two planes I found useful. Now I'm going to get the green vector by an alternate approach. So this is a different way of getting this green vector. So most of this is the same line, plane orthogonal to the line, spanned by the two normals n1 and n2. Goal vector is position vector to the point rho that we want to project. We want to get the projection, we want to get this green vector a different way. So here's how we're going to do it. It lies in this plane, and this plane is spanned by the two normals n1 and n2, so it has to be a linear combination of n1 and n2. So this statement. The black vector is the orthogonal component, so it's U minus this stuff, or U minus this linear combination. If I take the dot product of this black vector, which is what this stuff is, with either of those normals n1 or n2, I'm going to get 0 because this vector is orthogonal to the plane. And so that gives me two equations. n1 dot the black vector, n2 dot the black vector, and those dot products are both 0, and I can solve for these coefficients a and b. If I put those coefficients back into this expression for the black vector, I get this vector. If I add the black and the blue, A is the blue, I will get the yellow vector, and its components are minus a fourth, minus a half, 7/4. Now I'm going to employ what's called a non-orthogonal projection. Let's look at figure 8. Figure 8 is the same as figure 6, except it's got one more vector in it, this orange vector. Everything else is is the same, but we do the calculation slightly differently. U is this goal vector. I'd like to project that into the plane in such a way that I get this orange vector whose normal component is the yellow vector. This orange vector lies in the plane, which is orthogonal to the line, which is spanned by n1 and n2. So a linear combination of n1 and n2 should give me this orange vector chosen in such a way that its orthogonal component, which I call vector C, turns out to be this yellow vector. Orange, yellow, orthogonal. Now, how are we going to make that happen? What conditions can we apply to C? Well, this vector points to the projection point on the line. So it's got components C1, C2, C3. If I dot that vector with N1, I get the equation of the first plane. I get the left-hand side of the equation of the first plane, and that has to equal 1. And if I dot this with N2, I should get the number 2. So that's how I'm going to compute alpha and beta. N1 dot this vector C is 1. And 2 dot this vector C is 2. I solve for alpha and beta. I put those numbers back into the expression for C, and I write as a row vector to save some space, minus a fourth, minus a half, 7/4. This was the secret that I was trying to understand by jogging my memory for all the different things I had been stored in my head about projection. This was new to me, this approach, and that's why I drew all of these pictures to understand better what this alternate approach to projection was all about. My first recollection or first insight into this dot product with C was not the explanation I gave here. This came second after I pondered for a while. First thing I thought of was down here. C has to be the sum of this black vector and this blue vector. So when you think about that, if you take the dot product of that sum with one of these normals, N1 or N2, N1 dot the black vector is 0, and all that's left is N1 dot the blue vector, which is A. That I could calculate, and I calculated it to be 1. And here when I dot with N2, same thing happens, and I can calculate N2 dot A, and I get 2. And then I pondered, why is that 1 and why is that 2? And eventually it dawned on me the reason why this dot product is 1 and this dot product is 2. There was one more thing I wanted to reassure myself before I went anyplace else with this problem, was that the projection of the green dot or the goal vector down onto the green vector, which is the orthogonal projection, was indeed a minimal projection. So this is the green vector. Did that before. This is the orange vector. The orthogonal component, length, square root of 2. That's minimal. Orthogonal component, that's what this yellow guy is, turns out to be this, which is greater than the 1.4. So indeed, this green vector is still an orthogonal projection, minimal error from here to here. So from here to here is greater. Well, there's one more example I want to look at. And that's an example in R4 where I can't draw pictures. So this example jump to the intersection of two hyperplanes. Because of this 3 here and this 5 here, it's not a subspace. Again, the word affine could be used. I want to project this point, 1, 2, 3, 4, onto the intersection of these two hyperplanes. Notice the order of the variables w, x, y, z. I'm going to solve this in several ways, and here are some of the preliminaries that will help us carry through. I'll do a restart, define the position vector to the point u that I want to project. I will work in the student multivariate calculus package. I will invoke the linear algebra package for one command, define the constraints and the normals to these hyperplanes. Take the gradient. You'll get these normals, and you know that they were orthogonal to the planes. We know we can get a solution from Lagrange multiplier technique. So this is the position vector to an arbitrary point, wx, y, z, minus u, this position vector here. The norm of that is the objective function that we want to minimize. We're minimizing the distance between some point and u. Constrained, this point is constrained to lie on this plane defined by these, constrained to lie in this space defined by the intersection or combination of these two constraints, variables. And here is the answer. 1 minus 2 halves, 3, 1/2. Now, can we get a solution by this non-orthogonal projection technique? The calculations should be the same as they were for the example in 3D where we could draw pictures. Linear combination of the normal vectors gives us a vector equivalent to the orange vector. Subtract, that's the vector c. Then n dot c should be 3 here, and n dot c should be 5 here. Solve for alpha and beta. Put that back into c. I've defined c over here. And then print out the answer as a row vector to save space. And it's the same as what the Lagrange multiplier command gave, except this is a list and this is a row vector. So that non-orthogonal projection technique generalizes over higher dimensions. The last thing I wanted to check was, how does orthogonal projection behave in R4 where I can't draw pictures? But I have figure 6, which was drawn in R3. Can that guide me through the calculations and lead me to a solution in R4? Well, I needed a projection matrix that projected onto the space spanned by n1 and n2. Then that matrix times u, and we know what u is. That's the goal vector pointing up to the green dot, but in R4. The difference should be the equivalent of this black vector. And I want to add the black and the blue. I want to make that sum and see if I get the yellow. But what was the blue vector? What really was the blue vector? It was the vector from the origin to the fixed point on the line. What's the equivalent to the fixed point when you have these intersecting hyperplanes? And I said, okay, it's got to be the shortest distance. It's got to be orthogonal. This plane is orthogonal, so it's in this plane. So it has to be the minimum, it has to be pointing to the closest point to the origin in the intersection of the two hyperplanes. So if you go back over here to the Lagrange multipliers, this gave us the distance between u and an arbitrary point. If we let this be 0, we are getting the distance from an arbitrary point to the space spanned by these two constraints. It will come back as a list, and I convert that to a vector, and I say that ought to be the blue vector. And the black and the blue added together should give me the same solution that I've gotten twice already. 1 minus 3/2, 3 1/2. So whether I project with this non-orthogonal projection or with the orthogonal projection, and whether I'm in 2 or 3 dimensions where I can draw pictures or higher dimensions where I can't draw pictures, the pictures give me the pattern of what to do in the higher dimensions where I can't visualize what's happening.